This is a bit what I got from George Fliege when I got invitation to be able to give a talk here. Basically, there were three objectives: emphasize current challenge faced on the way that we operate now, and there were a set of questions that you wanted actually to be answered. So I would like to give special thanks to Adam, to Tim, and to George and John Tolan for allowing me to come here today. It is not normal that we make presentations addressing so many mathematicians, and I wanted to always to take the opportunity to be able to address such an audience, because we are extremely interested in cooperating more and more with mathematicians. So the objective, which I was given, it is the number 2, to emphasize the current challenges faced and to show the existing gaps in both technology and knowledge. But I thought I could not do that without telling you exactly what I do in the European Space Agency, which is the first part, to show the state of the art in which areas we are working, in which problems types we are solving, and what are the current solutions we have. But I'm also taking the opportunity today to give you the subject number 3 and number 4. Number 3 is to explain how ESA research and development project works, in case somebody is interested to cooperate with us. And number 4 is actually to encourage professors to partner with the European Space Agency. So again, thank you very much. I have divided the presentation in 4 blocks. The first block is I'm going to talk about optimization problems in ESA, how we face those. The second block, it is basically what it is going on wrong and what we need else. The third part will be research and technology, the process, how we let contracts and how you can access funding from the European Space Agency. And finally, how you can actually really partner with ESA in case you're interested. So my name is Guillermo Ortega. I'm the head of the Guidance, Navigation and Control section of the European Space Agency. My job basically is to control satellites and rockets in ESA. So I'm providing expertise, specialized expertise in the 3 areas: in the area of guidance, in the area of navigation, and in the area of control. And we are controlling almost all types of vehicles you can imagine that they are flying in space. This is a picture of what it is right now, what we are able to control and navigate and guide right now. So we are able to control rockets. You see here a picture of Vega, which was recently launched a couple of months ago. You have a picture of automatic transfer vehicle, which is resupplying the International Space Station. You have a picture of a vehicle dropping a little probe to study Mars or Titan or any planetary environment. You have also a picture of station keeping. Station keeping means collocate a spacecraft in one position and not to let it move in any other. You have also interesting problems in entry, descent, and landing, and finally problems in loitering. So basically circularizing around planets. All this we are able to do right now. So in ESA we are basically doing 3 functions. First of all is the guidance. So we plan the path of a spacecraft or rockets from one point to another. We do also navigation, which is the establishment of the knowledge of the current position of the vehicles. And finally, we do control, which is the matching between the guidance and the navigation, which is the establishment of the torques and force to be able to collocate the spacecraft in the right position. And this is a bit of the picture that always show when we are in a conference and how these 3 groups are working together. So we put a block of guidance, navigation, and control within another block called mission vehicle management. Because what we do also, it is something called failure detection, isolation, and recovery. If something goes wrong in any part of the spacecraft, we switch to a redundant channel and we will try to keep the spacecraft operating or the rocket operating. And this is rather important because there is no way you can manipulate a spacecraft once it is in orbit. So this is all the part of the work that actually we are doing. How many people are we employing to do that? Currently we are employing 3 kinds of people. The people of my section are called GNC systems engineers. They are in charge of designing and specifying, analyzing, validating, and constructing GNC systems. Then we have another kind of people that they take the control laws, the navigation laws, and the guidance laws, and they transform them then into software. And this software goes into the motherboard of vehicles. It can be a rocket or it can be a spacecraft. But underlying all this, we have another category of people who are developing for us the solvers, the propagators, the integrators, and all the mathematical apparatus that we have. And until now, we've been quite successful in partnering with the German companies, German universities, French universities, Swiss universities. Maybe now we have the occasion to also partner with UK universities. So which kind of problems are we solving right now? We are solving problems in the area of optimal guidance, basically trajectories. You think maybe trajectories are simple to do, but believe me, it is quite complex. We solve problems also in the area of optimal control. And we solve problems now, this is very recently, in areas called multidisciplinary trajectory of multidisciplinary design optimization, in which we are trying to design the systems at once, all of them at the same time. I will explain a bit about this in a minute. In comparison with these three main problems, the rest of the problems we have in space areas like thermal design or power design or design of logistics or design of testing, verification and validation of the systems are not so hard as the three first problems that I have presented. The first one is trajectory optimization. We've been doing this using nonlinear programmers. Actually, we've been developing in ISA already quite a lot of number of nonlinear program solvers. The problem it is the following: we need to design a trajectory that maximizes or minimizes some kind of measurements or a set of measurements with prescribed boundary constraints. Boundary conditions are, for example, target orbit, return or rocket stages, staging condition, visibility of ground stations. We have also included path constraints that are, for example, maximum dynamic pressure. We cannot reach a key dynamic pressure because the structure of the rocket or the spacecraft will break. We have also maximum acceleration. You cannot accelerate, for example, more than 2 or 3 Gs without breaking or cracking components. And we have, for example, path constraints. We use also performance index like maximizing payload, minimizing fuel consumption, and also minimizing cost. So you see there is quite a lot of variety of problems, and most of these problems I will explain to you, they cannot be solved at once. They have to be solved partially and gradually, and they are solved by stages. And this is a bit of the problem that I'm going to talk about. You can see here what are the kind of problems we have in the different branches of the trajectories. In the middle, you have right now the current solution, and in the right, I have put the degree of satisfaction that the engineers have solving these problems. For example, in ascent trajectories, right now we are using nonlinear programming solvers, and we are using local optimization. If I insert a huge number of constraints during a rocket flight, for example, I want to compute the performance map of Ariane 5 for the new Ariane 6 or Vega launcher, it will take me quite a long time, and we do it by stage. We include constraints. We cannot include all the constraints at the same time. We have to be quite stringent on doing these kind of things. The degree of success is relatively high because the flight of a rocket is very small actually. So the rocket flight, it is very powerful. It starts from the ground and it finishes when you deliver a payload, and it's about 20 or 35 minutes, maximal maybe 40 or so. So our degree of satisfaction is relatively high. In the area of entry, descent, landing trajectories, we can enter on the Earth or Mars or any planet. We are also using nonlinear programming and local optimization, and our satisfaction it is medium. Not all the trajectories are allowable. You have to take into account that we cannot reach a certain amount of temperature in the shell of the spacecraft or a certain kind of acceleration, g-forces, to be able to not to break components, and not all the trajectories that we wish are actually possible. So there's always a very complex design between the guy who does the trajectories and is able to do the optimization of the trajectories, and the guy who is actually doing the thermal system, the structure system, and the mechanics system. And all these people, they have to work together to be able to find a solution, because we are not able to optimize everything optimally. In the case of interplanetary trajectories, Adam asked me before how many of these spacecraft you have right now. Right now we have about 5 spacecraft. There are not so many. We are still using nonlinear programming, local optimization, and we do it by segments. We are going to launch a spacecraft called JUICE. This spacecraft is going to fly to a moon called Ganymede. It's one of the moons of Jupiter. We cannot arrive to Jupiter in a reasonable amount of time, and because the rockets that we have are not so powerful, we need to do a lot of flybys. And doing a lot of flybys, you need to fly around many planets and many moons. And we are not able to optimize in one go the entire trajectory. So what we do is we take the trajectory, we chop it in segments in the surroundings of the planets or the moons, and we optimize locally only one part of the trunk, in such a way that we have to join the parts of the trajectory arcs manually. And this is not optimal at all. So our degree of satisfaction is rather low. Rendezvous and docking trajectories. Rendezvous, it is about joining 2 spacecraft together. We've been doing this now for something like 6, 7 years. We are mastering now rendezvous and docking trajectories in circular orbit, not in elliptical orbit. We have no solution right now for the problem of optimal rendezvous. Optimal rendezvous taking into account conditions like lighting, where the sun is, where the moon is, or where the ground station is, which altitude you are going to have to maneuver, and so on. So our degree of satisfaction is very low. We are trying now to go further and see if it is possible to partner with somebody who would like to help us in the area of real-time trajectory optimization. For this, our goal it is to be able to optimize trajectories in real time. Real time for us means about every 1 or 2 seconds. We would like to be able to optimize the entire trajectory every 2 seconds. There is right now no technology to be able to do such a thing, but this is needed in case something goes wrong and we need to retarget the trajectory in re-entry systems or in ascent systems. Also works for rendezvous. So our degree of satisfaction it is actually very low. What are the objectives of GNC techniques in ESA? We have 4 main objectives. First of all, it is to minimize the vehicle propellant mass. In general, the overall mass, because we reduce the mission cost. The rate per kilo in a rocket is extraordinarily expensive. If you reduce the fuel and you reduce the mass of your vehicle, you reduce a lot the amount of money you need to pay. Second one is increase the accuracy of the control when tracking or regulating the plant. It's very important. If one of our scientists is looking at a star, which is very far away in a different galaxy, the pointing stability of your spacecraft has to be very high. So this is a very second important objective. The third one is to increase the agility of the space vehicle maneuvers. There are some missions in which we need to turn the spacecraft very fast, and this is one of the main objectives. And the last one, it is in general facilitate the overall design process of the GNC to make it more competitive and cheaper. This is basically what we do now. So we have 2 kinds of problems in control, in optimal control. First one, it is what I call the servo control, and the second one is the regulator. The servo control is a very easy problem. It is going from one point to another. You have a spacecraft that is looking at a star, and you want to change the spacecraft and to look at another star. This is called the servo problem. The second problem, it is the regulator problem. You are looking at a star, and you want to point at this star for a very long period of time, because you are interested in an observation. And there's a lot of perturbations in your spacecraft, coming from all kinds of strange sources, and you have to maintain the spacecraft in the same point. Why control systems for space are complex and are difficult? For us, it's very difficult to come with an analytical model of the plan. There are many perturbations. The perturbations are not linear, and the control most of the times is multiple input, multiple output. That's the reason these models are extraordinarily complex. There is also a high complexity in the description of the inputs and the outputs of the system. The system is dynamically changing. We are using permanently fuel, and every time when we are using fuel thrusting along the time, the center of gravity and the matrix of inertia of the spacecraft changes all the time, and it makes the whole thing adaptive and quite complex throughout the time. And then in case of optimal control, the theories, the robust control theories that exist now, they offer a partial solution for multivariable control systems. So our degree of satisfaction is relatively moderate. This is about the same thing, the same table in the area of control. Rocket control, we do mostly now bank control. It's relatively simple. We are now moving towards a bit more complex problems like linear parameter variant or quantitative feedback theory, but this is basically what we do. The control of the rocket, it is not so extraordinarily complex, and we are relatively happy with it. We can control such a vehicle. In the area of entry, descent, and landing, we are mostly looking into the area of predictive control, and our degree of satisfaction it is quite low. We need to have more understanding how to be able to predict a control entry in a planetary atmosphere. Planetary atmospheric flight is quite complex, and we are still a bit dissatisfied. In the planetary cruise, it's relatively simple, because what we do is we just fly by between the planets, and the thrusting arc of each of the flybys is relatively small. It is the trajectory optimization is done in such a way that the thrusting it is not so high in order to be able to shave fuel. So we are relatively content, because this kind of maneuvers that can be really well done. In the area of rendezvous and docking, we have explored a lot of robust control. So ATV docks to the International Space Station, fully automatic, and we use H infinity to do the control of ATV, and the compound ATV plus ISS. So we have already done that. This is a minimal control, and we are relatively, but this is still non-optimal. In the area of pointing control and stability, we use mostly PID control. It's very classical, it works well, and so far there have been no complex missions in such a way that it cannot be used. But there is something now coming up that everybody wants to have, which is introducing a huge amount of complexity. So in the 70s, 80s, 90s, we've been developing high thrust, either liquid or a solid, in which you are thrusting for a relatively small period of time, and the thrust is very high. Now everybody wants to move to low thrust. The reason why everybody wants to move to low thrust is because the fuel that you need to be able to propel your spacecraft is one fraction of the fuel you need to do high thrust. So since everybody is moving to low thrust, we have a big problem, which is low thrust trajectory optimization and low thrust control. In general, we are using now nonlinear programming, and we are using local optimization. Our degree is actually very low, and we need a lot of help in this area. I put here a bit of a timeline of what I think is going to happen in the next 10 years. So when we are making the research and development plans for the European Space Agency in the area of GNC, and I look ahead in 10 years and I see what's going to happen in 10 years. So you have here, we would like to have GNC on one go. We would like to be able to design a GNC in one go in such a way that we don't need to touch it after the design. Right now there are several cycles of design until we get it right, and we get it right. We would like to have very high precision landing. Right now, when you see in the television or in the newspapers that NASA or JAXA or anybody, the space agency has landed with high precision, for them high precision means 100 kilometers error. We want to land with 10 meters error or 1 meter error. This is what we call pinpoint landing, and this is a very, very big challenge for us. We want to have also elliptical rendezvous. Everybody knows right now how to do a rendezvous in circular orbit, because the equations of motions are linearized in circular rendezvous. When we move to elliptical rendezvous, the equations are a complete nightmare, and we need a lot of help to be able to do optimal rendezvous in elliptical orbit. So I would be willing forward to be able to put money on that. Another challenge is called GNC on a chip. We would like to be able to have a GNC system which is only working in a small FPGA, a very small chip. This is for us a challenge, and we would like to be able to go towards this. Then another challenge is automatic multibody. When you have a satellite which has a lot of appendages, huge solar arrays, or huge antennas, we would like to be able to control all this in one go at the same time and easily. And finally, what we call integrated GNC, everything inside one single box. How does it translate this into mathematics? And that has been quite of a challenge for me to be able to try to convey the message. In the area of control engineering, we would like to be able to have help on nonlinear systems. And look at all these techniques we are looking around. We are looking for universities or people who would like to be able to give us help on nonlinear dynamic inversion, feedback linearization, sliding mode control, numerical optimization. This is very much now needed. We have already done some work on fuzzy logic control, neural networks, and we are exploring now with the University of Dublin something called web-based control. It's a professor at the University of Dublin which it has a technique which is very promising. We would like also to focus on control of distributed parameter systems and also put humans inside the control loop to see what is the interaction between a human or a machine. This is basically the challenge in the control engineering area. I put here, this is a bit difficult to read, but you can have the presentation later on. The control techniques versus what we have already analyzed. You have control on linear time invariant plants, control on nonlinear time invariant plants, flexible plants, multi-body distributed systems, and faulty plants. And what are the techniques that we have used to be able to give a solution to these problems we have. Not all the crosses are available, not all the crosses have been studied, and it could be a good idea that perhaps we get some more help from mathematicians to do that. One important aspect is control reconfiguration and failure detection, isolation, and recovery. For us, it's very important to have controls autonomous and automatic. So we cannot send somebody to repair some faulty plant or electrical system or whatever. So we have to be able to be robust to failures. And this is for us one of the main priorities. We are raising now technology in this area, and we are putting relatively a good amount of funding. So I would like to challenge you to come back to me if you are interested. Numerical optimization, it is something we want to explore very much. It's a combination between optimization techniques and basically parameterized systems of the spacecraft. We're also very much interested in it, and if somebody has an interest, I could appreciate to have a contact. what are the mathematical challenges I see? I would like very much to have an universal transcription method. We talk about that. We have now the possibility to continue with something called transwarp with the people of the University of Bremen and perhaps now Stuttgart and maybe perhaps you or somebody else. And we are looking forward to be able to have a transcription method which can be applied to almost everything. So we don't have this. We would like to have very much multidisciplinary optimization. We would like to be able to design a rocket from scratch in one single go. Right now, to design a rocket, it takes a lot of time and it takes a lot of people from many disciplines. I would like to be able to cut down the number of the people and the cycle of the design of the systems. This is for us important. Another subject is true global optimization. I would like to be able to have a system or a software or a program which allows me to optimize a trajectory to go to Ganymede in one go. And this trajectory should be as short as possible and it should give me the maximum payload as possible. And this is very difficult to do. Then another problem it is optimization on a chip, to be able to put an NLP solver inside a CPU or inside an FPGA. This is what we need. We need to embed the system inside. And then the last challenge is to have all this with safe trajectories with humans inside the spacecraft. I put here a bit of the challenges that I saw to convey the message today. My first challenge could be global optimization, obtention of a true global minima in a very large search space. This we don't have right now. There has been a conference in global optimization in Amsterdam, and they were also looking for challenges, solutions. There has been a lot of discussion, but we have to make this happen, really, and we have to make this to arrive to our workstations. Transcription methods. We need to have transcription methods, optimization, into algorithms that can actually be solved. I don't know how to do it. Real-time optimization, optimize a real time, for example, every second. If there is something wrong or there is a branch trajectory and I want to change my re-entry and not land in one particular point in the Earth, but I want to land in another point in the Earth, I would like to be able to calculate the trajectory in real time every 1, 2, 3 seconds. Multidisciplinary design, optimize all spacecraft subsystems at once. This will save us a huge amount of money and a huge amount of manpower. And then finally, hybrid optimization, to be able to combine several solvers at the same time, depending on the problem and depending on the needs. This is where I think that the money should be invested. So, if I may continue quickly, we have ESA has, since the beginning of the agency, which was founded in 1975, we have an extensive research and development program. It's very well described. We have different service domains and technologies domains. Maybe you don't understand this so much, but maybe I'm going to put perhaps a view graph which could be a bit more illustrative. Those are basically the programs we have. We classify the technologies in technology readiness level. The readiness level 0 means the technology doesn't exist. The readiness level 9 means the technology is fully proven and is already flying. Per each of the technology readiness level, we have a different program. And TRP starts in TRL levels 2 and 3. Then you have from 4 to 6, you have CTP, GSTP, OP, ARTES, Genesis, Evolution, FPP, Aurora. All these programs are depending on the kind of a spacecraft or the kind of missions you are talking about. So in some of the occasions, the programs are optional and they are driven by the delegations of the European Space Agency. In some others, the programs are mandatory and the funding actually it is controlled by the European Space Agency. In this particular case, I would like to draw your attention to GSTP6. The United Kingdom has made available right now 35 million euros in GSTP6. There is a great opportunity for mathematicians from other countries or other member states of the European Space Agency. So the GSTP activities aim at the pre-development, if needed, of qualification of identified technologies required by future space projects, and the feasibility of those technologies having been demonstrated by TRP or national or international R&D programs. So we have observation of the Earth, science, human spaceflight, space transportation, and generic technologies and techniques. And basically the last one, it is the one that it can be applicable for mathematical research and development. There are 4 elements on GSTP6, and there is a possibility in element 1 in which the agency initiates an activity with industry or with academia. In the element 2, it is the university or the academia who sends a proposal to us. This proposal is evaluated and you get a contract awarded. So it is not so. Element 3, it is a flight opportunity if you want to prove during the flight one of the technologies. And element 4, it is especially formation flying in elliptical rendezvous. It is especially for program. So how could you partner with the European Space Agency if you wish, if you wanted? There are several ways to access funding from the European Space Agency or partner with ESA. The first one, it is in technology research program. It's a very low TRL level. If there is a technology which has a very low TRL level, we put an activity on TRP, and the university or the company has to send a proposal, has to bid, has to compete with the rest of the nations, and you get access. If you win the proposal, you will get access to the funding. In GSTP, it is a bit different. GSTP money, it is controlled by the delegations. So it depends on the delegation. If they would like to be able to finance your activity or your idea, you will need to be able to get permission from the delegations. And there are two methods. The method one, it is that we raise an opportunity for research, then we put it, and then you apply for it and you win the contract. The method number two, it is you send us a proposal, which is about 10-15 pages with the idea. Then we say, okay, we are okay. Your delegation, the delegate of your country is okay, and we award the contract. It's a bit more straightforward. There is another way, if you wish to collaborate with us, which is called Network Partner Initiative. The European Space Agency has put a nice program to create PhDs in Europe. And we are financing up to 50% of your PhD with a ceiling of 30,000 euros per year during 4 years. There are 2 calls every year, one in spring and one in autumn. It can be any idea. We will finance your PhD for the maximum of 4 years, and there will be a maximum of 2 stages of 6 months each at ESTEC during the PhD. So the condition is that the PhD has to be with a professor in university, and one of the companies of Europe or the European Space Agency has to back up the research. The idea it is to form a person as a PhD, and the idea it is that this person, if he makes a patent or he makes a discovery, it remains in the company. So there is a link between companies, universities, and the European Space Agency. The next call for ideas is October 2013. If you are interested, please contact me, and I will see how could it be possible to do something together. There is also a possibility of collocations at ESTEC. We have several ways of collocating people. We can collocate professors, we can collocate students, we can collocate PhDs or research fellows. So if you're also interested in being in ESTEC for a while, please let me know, and it could be possible. Or if you have somebody who would like to be able to do an stage, paid or unpaid, for 6 months in ESTEC next year, I'm free and available to discuss. This is about the last one that I have. I wanted to go back to the first one for the challenges. So this is basically what I wanted to say. I don't know if I have conveyed the message in an appropriate manner, and if I have encouraged you to come to our field of research. It is completely different from areas we have discussed before, like banking or logistics or so. But okay, I think it is worth. Been working in the agency for 21 years, and the number of PhD students and the number of projects we have in the area of optimization has been increasing ever since. Thank you. Almost in time.
Yeah. Any quick questions? I've got this one. Could you put the slide up? There was one slide that mentioned linear matrix inequalities. It was something to do with numerical optimization, and there's a lot of people here that would be interested in that, I think.
Am I?
Yes. I think it was entitled numerical optimization or something like that.
Yep.
That one.
So we have made an LMI toolbox with one university in Canada. Canada is also a member state of the European Space Agency. It's an associated member. We have an LMI toolbox, and if you are interested to continue, I will be ready to prosecute it, of course.
Okay.
The toolboxes that we do with the universities, they are most of them open source. So we do it for the rest of the community, for the rest of the for the space community, and we don't charge for it unless there is a need from university to be able to sell it commercially. So in that case, also it's not a problem. But we are very much interested in LMI.
Thanks very much. Yeah.
Okay.